Okay, very good. So thanks, Professor Taylor. Graham Taylor is a professor on Canada Research Chair in Machine Learning at the School of Engineering in Canada at the University of Guelph. Okay, he's also the Research Director of the Vector Institute for Artificial Intelligence, and he's Academic Director of NextAI. I think maybe it's a company or a startup specialized in AI. He leads the machine learning research group, and he's a well-known researcher. He's done a lot of interesting research in machine learning, in deep learning. I reached out to Professor Taylor because he did some research on biodiversity. So maybe he'll come back one day to show us what he has done. But today he wants to share some very interesting research on using models to learn about other models. So he's going to explain you what it is. So this about so the title of his talk is Reducing Deep Learning Compute by Hypernetwork-based parameter prediction. I believe this is some research that he has done with people at Meta or Facebook, if I'm not mistaken. So thank you very much for talking to us, and probably we can give you like 30 to 40 minutes, and then after we can open the floor to questions. Okay.
Okay, that's perfect. Thank you for the intro. It's great to be here, and I appreciate people coming at the end of the day. I know most of you are based in New York, so just Eastern time like me. And just a clarification, just want to say NextAI, it's a non-profit incubator for AI-focused companies, and it's open to anybody around the world. So if you're starting a company and you're interested in building it in Canada, because we have a great AI scene, it's something we're known for, maple syrup and AI, please check it out. Just look it up, and we have funding. We seed all our companies with $50,000, but there's up to $250,000 in seed funding that is provided by donors, and we have an excellent network of mentors. We have world-class instructors that lecture in the program. It's an interesting founder development program compared to other startup accelerators, because we have a very academic focus and bring in professors to teach on the technical side. I teach some courses myself, a number of my colleagues teach, and we also have amazing business professors that come in and teach, that come in from the US and all over Canada to be part of it.
Graham, and you said it's open worldwide, not just for folks in Canada, or worldwide for folks who want to start their company?
So Next Canada is the organization that runs the program, and its original program called Next 36 was focused on only Canadian founders. Yep. But NextAI, when the program was started in 2016, we took an international view. And so as long as the companies come to Canada, participate in the program, they can come from anywhere in the world.
Cool. Super cool.
Thank you.
Okay, so I will get started. So as I said, I'm going to start kind of slow and historical. So looking at the past 10 years, deep learning has really dominated artificial intelligence, and it's quite apparent by deep learning's adoption in industry, like particularly the high-tech industry, and also the level of hype in the mainstream media. So just very briefly, what is deep learning? It's the modern practice of neural nets. Some might call it modular differentiable computing. And it's built on the backbone of a technique called learning by stochastic gradient descent. So learning gradient descent is an optimization method, and it's really at the core of deep learning. And I'm going to come back to it later, but that's particularly, it's a iterative algorithm which results in training models maybe days or weeks or even months. And this is precisely what we're going to tackle in this paper. So what's fascinated me for a very long time is that a lot of the deep learning backbone is built effectively on 80s and 90s technology. So for example, the backpropagation algorithm, which is a core subroutine of stochastic gradient descent, convolutional neural networks, very popular type of architecture for processing images. This is all very old school technology. And around, some would maybe argue 2012, 2013, 2014, things started working. This old technology started delivering amazing results. And the kind of 2014 view of why stuff had suddenly started working was that as time went by, people obtained more data and more computing power, and this allowed the capacity of machine learning models to grow accordingly. So this is a plot that Marco Aurelio Ranzato showed a number of years ago. I always liked it, though, it's showing sort of what happens when you push out on the data, you push out on the GPU computing power in terms of flops per second, and this allows you to grow your models. And really the introduction of general purpose GPU computing enabled by NVIDIA's CUDA library completely changed the scene. And I remember being a grad student in 2008, 2009, when CUDA came on the scene. And this really enabled cheap personal supercomputers that are highly optimized for the types of computations that are performed by these deep learning systems. So the data and the compute have enabled much more complex architectures. And it's not that those architectures couldn't have been envisioned in the 80s and 90s. It's just we weren't able to train them on so much data and in so little time. So this 2014 view of deep learning and why it suddenly started working was based on the premise that until about 2012, the models were just premature. So we didn't really have enough data and enough flops to train them. They'd overfit and be slow to train. And the community often talked about getting stuck in local minima because it was a non-convex optimization. And a lot of focus was placed on scale. As we continue to scale compute power and data, we could grow models more and more. So we really needed scalable methods. If we jump forward a few years, a more modern view is that local minima weren't really ever the issue. And in fact, something magical happens when we scale models to a certain capacity. Okay, so making them more complex, adding more parameters. The purple curve here shows how test error, so test error is sort of the proxy for generalization, the thing that we really care about. As we make a model more and more complex by increasing its width, that's on the x-axis, we see that performance first improves. So this is the drop in error and the drop of the purple curve. And then it gets a little bit worse, and then it drops again and starts to improve. So neither the classical statistical view of machine learning, which is if you add too much capacity, you're going to overfit, that's in the green line, or the modern view of machine learning, which is just keep adding more capacity because that's what you need, really are upheld in this view. So there's another plot. Both of these are from an open AI paper from a couple of years ago. This shows that this phenomenon, which is called double descent, it leads to a regime where bigger models actually become worse for a period of time. So again, the x-axis here is growing the capacity of the model, making it wider and therefore adding more parameters. But the peak in error occurs, which is around a point called the interpolation threshold. And this interpolation threshold is the point at which the model is just barely big enough to memorize the entire training set. So this is kind of an open research question, this transition point between sort of the classical regime of how we once understood machine learning and the modern regime of sort of deep neural nets and adding lots of capacity. But again, just to summarize, this understanding is there something magical about big models? Now, there's a romanticized notion that deep learning is the end of feature engineering. Deep learning was the point at which we stopped spending a lot of time, extracting features from images, for example, like edges or color features, or designing all these fancy things like SIFT, and just started feeding pixels directly into deep learning models. So we've heard this story, and there's no doubt that feature learning has reduced the need to design features by hand. But in step with performance, models have become sufficiently more complex, not even in the notion of many parameters, but also in their design. So Stephen Merity, a number of years ago, made this claim that architecture engineering has become the new feature engineering. And for a number of years, we were able to sort of push more and more complex models and realize performance gains. So here in this plot by Eugenio Curlichelio from Purdue, we can see on the x-axis, this is another notion of the complexity of a model. So this is gigaops, or the amount of cycles it takes to sort of push images through a visual recognition architecture. So as we add more and more giga operations and make our model more complex, for a while, the models got more and more performant, as measured here by the top 1 accuracy on ImageNet. So we improved over AlexNet. We improved over the first inception network, GoogleNet. Then ResNet came along and we sort of pushed it. We started doing more and more architecture design and adding more capacity. But eventually, this is circa 2018, we started to plateau. And perhaps this was sort of a limit to human ingenuity in architecture design. This doesn't, because this plot is from 2018, it doesn't capture some of the more modern architectures that are built on vision transformers and so forth. But the point here still holds is that there is some limit in terms of what people can do, and people have started to move towards more automated architecture design. So I saw a talk, actually the Toronto Machine Learning Summit back in the fall, and this is given by Frank Hutter, who did this really nice framing of deep learning 1.0 versus deep learning 2.0. And Frank's view of deep learning 1.0, which you see here in front of you, is very much this sort of manual architecture engineering targeted towards a single metric, which tends to be performance. If it's image classification, its accuracy is the performance measure. And this is exactly what we saw in the last plot. We're measuring performance versus complexity of the model. So there's a human bottleneck here. The deep learning expert who designs this architecture manually optimizes the hyperparameters, and compared to traditional machine learning systems, these deep learning systems are trained end-to-end to maximize performance, but there's this very costly trial and error process that ignores all other considerations, the ones that we see on the right, like fairness or robustness or calibration or interpretability, latency and memory, and so forth. So Frank's view of deep learning 2.0 is the automation of the deep learning pipeline. So the deep learning expert is replaced by an auto machine learning system that employs meta learning and optimization over the architectures and hyperparameters. So you're taking the work that the deep learning expert did, you're handing it over to automation. And the nice part of this is that it requires no specialized machine learning knowledge to use. It provides very clean interfaces for users to specify different objectives, for example, fairness or robustness or interpretability. And there is no need for an expensive deep learning expert to be inside the inner loop of applications. So Frank's argument is that it boosts productivity for domain experts and even deep learning experts. But its main requirement is compute. Frank presents a positive view that compute improves over time. GPUs get better, CPUs get better. We invent fancy deep learning processors like TPUs and so forth. But I'm going to take a slightly different view in that there is a bottleneck at the core of the system, and this is stochastic gradient descent, the training of these models doing thousands or millions of iterations. And this kind of automated search over the space of models, it means potentially training millions of architectures to convergence, measuring their performance, and then throwing them away. So it's even if a computer is getting better, it's still very wasteful. And this is an AI for good group. And so burning a bunch of cycles and increasing carbon footprint is not necessarily a good thing, even if it reduces reliance on deep learning experts. So what I want to talk to you about today is really this question that was proposed by my PhD student. Actually, he's just graduated, so I should say former PhD student. He's now moved to Montreal, is working at Samsung Research. His name is Boris Kniazev. And he, during a research internship at Meta, which used to be called Facebook AI Research, had this idea of whether maybe we could just replace these iterative optimizers with another neural net. And this neural net is a type of meta model called a graph hypernetwork. It accepts as input a computational graph, and spits out its parameters in a forward pass, which is basically less than a second, produces the parameters without having this iterative, expensive training loop of SGD. And it sounds a bit crazy, but it actually works. And so for an architecture it's never seen before, which is a ResNet 50 in this case, it can output all 25 million parameters and achieve 60% accuracy on CIFAR 10 with absolutely no training at all. So 60% accuracy on CIFAR is by no means a state-of-the-art result. It's very easy to get 95 plus accuracy on CIFAR, but a modestly performing net has many uses. For example, inside this architecture search over different models. So that's the intro. Now I'll go on to the details. So from a human-centric AI standpoint, why do we care about this? Well, I mentioned before, as AI and machine learning becomes more prominent, there is a concern about the rising cost of computation. And most of this concern has to do with the iterative optimization of deep nets. So I argued previously that feature learning has supplanted feature engineering, and enormous human and computational effort is placed on devoted to engineering new architectures. So Frank Hutter, who I mentioned before, and others have promoted this view of auto machine learning as a way forward. So automating architecture design with tools like neural architecture search and reducing reliance on deep learning specialists. Yet neural architecture search, this process of automating the search over architectures, is often targeted as an extreme user of extraordinary amounts of compute. Others will argue that the problem is not so bad. So there's actually a paper that appeared out of Google in January or February this year. It's fairly recent. And they highlight the 4 M's of best practices. So the argument that these Google authors make is that others have sort of overclaimed the severity of the carbon footprint problem, and that some papers subsequent to this very off-cited University of Massachusetts Amherst study have misinterpreted the cost of running NAS as the training cost of the model that was discovered. So it's way, way, way more compute intensive to do the whole search over the model space. Training the final model that's been discovered is much, much less costly. The cost of NAS is obviously orders of magnitude more than training a single model. And the key argument in their paper is that the carbon footprint of ML is that training is shrinking, not increasing. And it's a result of these 4 M's. So let me tell you what these 4 M's are. So in this plot, we see sort of applying each of the M's in sequence and realizing some gain in carbon reduction. So first, they start with a baseline model, which is a sort of 2017 style transformer, like the first transformer paper. And they make an efficient version of this transformer. So the new transformer right away will get 4 times carbon reduction. So that's the first M, is better model, M for model. Then they say if you use newer generation hardware, so instead of using 2017 style GPUs, I think we're P100s at the time, you use a TPU V4, you'll get an additional 14 times improvement. So you're up to 57 times improvement in carbon reduction. So the next M is machine, so use better machinery. Then the next M is mechanization. So move to, advertising to you, a Google data center, not any old data center, but a fancy, efficient Google data center. You'll deliver another 1.4 times carbon reduction. And then if you choose a specific location of the data center that's connected to low carbon energy sources, you can reduce the footprint a further 9 times. So that's how we get to a total of 747 times carbon reduction by making these choices along the 4 M's. I should say the last M is map. Moving to a data center, say in Oklahoma. Okay, so while there's a bit of a debate over this in terms of the severity of the carbon footprint issue, the current approach to training networks using SGD for days or weeks, it's very expensive and it's wasteful. So the key point that bothered Boris when he brought this idea to us as his advisors was that every time you run SGD and you randomly initialize parameters, typical optimizers will just disregard all past experience that could be gained by optimizing thousands or millions of nets. And this is true in NAS. Like we waste a lot of experience gained in doing the optimization. So the question that we set out to answer is basically, can past experience reduce reliance on iterative optimization and its high computational demand? And this is actually orthogonal to Google's 4M. So you could sort of apply all of their strategies as well as this alternative to SGD. Okay, so here is how the technique works, and this is where it gets a little bit more technical. So we feed to our model batches of architectures. So that's what you see coming in on the left. So you're used to seeing, say, batches of data, like batches of images or batches of text documents. Here we're feeding batches of architectures expressed as a computational graph. So this might represent a ResNet or a vision transformer, or a specific flavor of these sorts of models. And these are fed to this type of neural network called a graph hypernetwork. And the graph hypernetwork takes this description of architectures and spits out their parameters. And so then we take the network whose parameters we just predicted and feed it images. Say you take ImageNet or CIFAR, your favorite data set, and you feed it a batch of inputs. You check this against the ground truth, you compute some loss. And then instead of backpropagating only through the network with parameters, you backpropagate all the way back through the graph hypernetwork, the one that's generating the parameters for the student network. And it's very much like meta learning. And we use a graph hypernetwork architecture that was originally proposed by colleagues at University of Toronto. But what their work wasn't really suited for unseen architectures. So I mentioned before, we could take a network, an architecture the network has never seen before, like a ResNet 50. That was our point here, is that we could sort of learn on a data set of architectures, and then at deployment time, present the model with a completely novel architecture, and then the graph hypernetwork could predict its parameters. And those parameters.
Graham, can I ask you something?
Of course.
So you mentioned that so it's very similar to meta learning. So meta learning, like there are different models. So where does it play a role? Is it when you combine these like different batches of models and you have like a single objective function, a single loss function for that, or?
Yeah, there's only a single loss, and the loss is whatever the loss is you're focused on for your task. So we conduct experiments on image classification. So specifically, we do experiments on CIFAR 10 and ImageNet classification. But really, you could be doing semantic segmentation if you wanted to, or you could be doing object detection, or you could be doing some other visual tasks. You could even be doing, you could be outputting the parameters for a graph neural net and doing a graph-focused prediction task. We're actually quite agnostic to the prediction, because we're just using whatever loss function is appropriate for that problem.
Okay, but this is like one task only. This framework.
It is one. Yes, I mean, this would be cool to do it in sort of a multitask setting, but it is one task, one data set. So what we're trying to gain is generalization over different architectures, but we're not trying to do any generalization over data sets at this point in time. This is sort of, when I'll get to future work, I'll say this is one of the things that we really want to do. But the graph hypernetwork, which outputs parameters, it is trained for ImageNet, whereas it's another one that's trained for CIFAR 10. It's for a specific data set and a specific task. And
the graph hypernetwork is general enough to can like simulate any network. Like, like let's say the vision transformers and all these kind of things. Anything that people could invent, it'll be in there.
I'll show you that. Actually, on the next slide, I'll show you the sort of what kinds of architectures we experiment with. But I should say that the original graph hypernetwork that was in this 2019 paper really wasn't up for this task. It couldn't really handle diverse architectures. So we do have a few enhancements, namely this sort of meta batching and virtual edges and parameter normalization, which I'll discuss later. But these are sort of additional improvements that we make to the graph hypernetwork. So we call it graph hypernetwork two. It's like GHN v2 versus GHN v1, and that's one of the contributions in this paper.
Okay.
Graham, do you mind if I ask one
go
question
ahead.
as well, since we stopped on this slide? Everybody always has questions on the same slide. The other thing I want to say is that for other folks, if you want to ask a question, feel free to raise your hand and I'll let you in. We shut off videos by default because we're having some spam problems. But so my question here is the big box with HD, that's your hypernetwork. And out of that, you're essentially sampling from that hypernetwork to say, hey, let's try this particular set of parameters on a fully built network. And then you run a batch of images through that and calculate a loss. Is that right?
That is exactly correct.
Got it.
And the hypernetwork, again, like I'll get into a little bit more details on it, but like at the very beginning, the hypernetwork would not be very good at predicting parameters because it's just getting started. So you would be getting very high loss at the beginning of training because you would be outputting like really crappy parameters and then, you know, doing prediction using those crappy parameters, but it will get better and better and better. And it only uses the loss on the task.
Got it. And so then it's almost equivalent to like a massive group dropout where you're like dropping out this entire potential architecture over here. Like, let's say you could conceivably have like a residual connection. You're just going to drop that entirely. And when you allow it to be in there, you're going to predict some parameters for it, or you'll just drop it out entirely. And thus that's an analogy. It's obviously not doing the regularization thing that dropout does, but it's predicting. The interesting thing for me is that it's predicting both chunks of architecture, like entire connections that may or may not exist, and it's predicting individual parameters for that. And that's a little different in my mind than, for instance, so I worked with Tony Zader for a long time, and he has this idea that one thing you might want to do is have a prior over the kinds of networks that might learn things and instantiate that prior, but then you have to learn, right? There's both innate kind of innate ability and then learning on top of that, but you're baking it all into one step.
That's right. Yeah, a couple of points on that. I mean, we have very weak priors on networks right now. Like when we do weight decay, right? It's a very weak prior that says you should like have parameters that are close to zero, right? It's like a Gaussian prior on the weights. And so this is like a very strong prior over the architectures because the prior is sort of embedded in the GHN. And it's a complex model, hypercapacity model. Yeah. And I think the analogy with dropout's interesting. That the most similarity I see there is, as you mentioned, like there's going to be sort of substructures in computational graphs that represent architectures that kind of are repeated, right? They come up over and over again. Yeah. And those parts will be like almost like the part of the activations that shows up in dropout repeatedly. And that's why learning works, is because there's sort of shared substructures across different architectures, and the GHN learns to recognize those and know how to deal with them.
That makes a ton of sense. Cool, thanks.
Okay, I'll have another slide on a little bit more detail, but this is just sort of like the gist of how it works. So another key contribution of the paper is the development of this DeepNext 1 million data set. So it's 1 million different architectures in what we call the in-distribution set. So that's at the far left. So so we have 1 million training architectures. That's what's used to train the GHN, 500 validation and 500 test architectures that are all sampled from the same distribution. But what we intend to show in this work is that at deployment time or test time, we can present the model with out of distribution architectures, ones that are vastly different than what it saw at training time. So we have an OOD data set of wider architectures than the ones it saw at training, or deeper architectures, or denser ones that don't use batch normalization when the architectures that saw at training time did use batch normalization. And also we have like very specific architectures like the ResNet 50 or the vision transformer that I mentioned. But the building blocks are shown below, like convolutional nodes, batch norm, aggregations like some, adding bias, even elements like multi-scale attention that's present in vision transformers. You can see global average pooling that's often used at the end of a network before a softmax. positional encoding, which gets used in transformer style architectures. So you can kind of mix and match these architectural elements to build fancy architectures. And the network structure is it's based on this framework called DARTS, which was used for neural architecture search. We've just expanded it to use some more sophisticated building blocks that show up in kind of modern architectures like vision transformers and so forth. Now, in terms of how we code the architectures, so at the input layer, this is what you're seeing now on the left. So each node has a one hot feature that encodes its primitive, the primitive being like max pooling, or whether it's an input element, or whether it's doing global average pooling. And then in addition to sort of the primitive, we have some additional features that describe its shape. So that's what you're seeing beside it. So for, you're seeing like in terms of the node 1, node 2, node 3, this would be, for example, an input layer followed by convolution, followed by linear bias, followed by pooling, then a 1x1 conv, and so forth, all the way till the end where you do global average pooling, and then you do a bias, and then you're basically at the output of the network. And these features are on the nodes of a graph, a computational graph, and this GHN is basically a big graph neural network that takes these node features, and then along with the structure of the graph, which are the connections between the different modules, the colored modules that you see here.
Okay. And so it can change the identity of any module, but also arbitrary connections between any point and any point, or no?
Yes, these are feed-forward networks. So, there's always an input, but it can do branching, like in ResNets, where you sort of go off in the residual and then come back. It can sort of do arbitrary feed-forward structures, but there isn't like recurrence in these graphs.
Okay, cool.
Are you using a specific library for these GNN? Do you have like some GNN libraries that that do this kind of things out of the box, or you have to program everything?
Yeah, so our dependencies, I think the only dependencies that we're using are Network X, which is just a general graph library. I don't think we depend on PyTorch Geometric or DGL. Like, we work with those libraries sometimes for doing graph neural nets, but I don't think we have dependencies on either of them. We have dependencies on PyTorch and Network X. I think those are the strongest dependencies that we utilize.
And you have your GitHub page, right? So people can have a look too.
I have GitHub at the end, and there's both the GitHub code, and then there's a demo collab notebook, so people can come in and just start experimenting with this right away.
Thank you.
Okay, so then I was telling you about this notion of OOD generalization. So when I describe these different shifts, what you can see here, like, we're evaluating the model on wider, deeper, or more dense nets than those at training time. That's what you see in these violin plots at the right. So on the top, we've got the number of nodes. So the distributions you'll see for example, the deep nets or the dense nets, they have a much more variable spread of the number of nodes compared to the set of training graphs, which are on the left in blue. And then if we look at the number of trainable parameters, you see the distribution on the left for the training set. But for these OOD test sets, some of them have several orders of magnitude more parameters. So it's these much larger models at test time, but still has reasonable performance. Okay, so I promised a more detailed slide. The training details, it's basically, again, learning to predict parameters by using gradient descents. And the reason that it works is that we're always doing these gradient descent updates based on the current architecture. And so we're likely to predict better parameters for the next architecture. And as we said before, like, there's this notion of sort of substructure sharing, because the training architectures are drawn from the same distribution. So we should expect to see these substructures. And so the GHN's ability to predict good parameters gradually improves over each training iteration. there's a plot here on the bottom left, which is showing sort of the V1 GHN, and then the improvements made by the V2 GHN. And I'll quickly go through some of these improvements. And then the objective function is shown on the right here. There's two loops. There's a loop over the batches of images. These are the ones that we're showing the architecture that's making predictions. And then there's a loop over the meta batches of architectures, which are the architectures that are being fed into the GHN. But as you notice, we're drawing architectures. These are labeled by A, and we're making predictions using the parameters predicted by the graph hypernet, that's HD, that takes the architecture, it has its own parameters theta. And so those are the parameters that get used, again, together with X, the input, to predict, say, a Y hat or a prediction, and then that's compared to the ground truth on whatever data set we're doing, and then we generate sort of the loss in the usual style. So for image classification, this would be cross entropy, and then we're just doing gradient descent based on that loss. So I'll go on now to the improvements. So I said there were three key improvements. One is this notion of virtual edges. So one issue with the types of graphs that we see with these computational graphs that represent architectures is that they often have the form of long chains. And we saw that in some of the visualizations. So what we do is we add virtual long-range connections to the graph, and we weight them based on the shortest path between the nodes. So this allows for better gradient flow. We weren't the first to use virtual edges in graph neural nets, but it really makes a difference in terms of gradient propagation. And the other thing we do is we use a separate MLP for the real edges and the virtual edges in the GHN message passing. So for those of you who are familiar with graph neural nets, we basically have sort of two sub procedures in the message passing step. And empirically, it works better if we treat these real and virtual edges separately. The next issue that we deal with in GHN2 is that these iterative optimizers that aim to stabilize the variance of activation use initialization tricks. And hypernetworks have pretty extreme problems in terms of their stability, and they have this, they're subject to exploding or vanishing activations. So you can't really stabilize them in the same way as sort of normal networks. And so to address this issue, we have these sort of operation dependent normalizations. So first of all, the convolution and fully connected layers use a fan-in scheme, and the parameters of the normalization layer, such as batch norm and the layer norm and the biases that are typically normalized as constants, are normalized using a squashing function. And so the idea here is that we try to imitate the distribution of models that are trained by SGD, because like we would like the models whose parameters are output by our GHN to look like models that are optimized by SGD. SGD is sort of like our baseline or benchmark. It takes a very long time to train models with SGD, but in terms of the parameter distributions, we would like to achieve parameter distributions that look like SGD trained models, because we know SGD works. It's kind of an open question of how far we can depart from models that look like SGD trained models, but we found that sort of keeping their parameters in the same ranges seems to lead to better performance. And so we can see here in some of the plots, models that are trained by SGD in blue versus models that are trained by GHN1, which doesn't use this specialized normalization, which tends to have high variance of activations in orange. And then our model in red, which is somewhere between the SGD trained models and the GHN1 models. It's the GHN2 is more stable than GHN1.
Do you interpret that as saying that GHN2 is then doing a better job of allowing a certain kind of variability and kind of keeping you maybe closer to the chaos threshold without falling off it into overactivation or underactivation? Or do you
Yeah, I
think
think that's a
there's
nice
still
way of
more
looking
work to
at it.
do, and like we should really treat SGD as the gold standard? Because the SGD tricks that we use, they feel like heuristics to me, right? And you can imagine
Yeah.
other ways to solve that problem while staying, say, near network criticality.
Yeah, it's a good point. I mean, the parameter distributions that we get from SGD are the function of all these kind of tricks that we throw at it. So what's to say, you know, that's the right distributions of the values of parameters.
Yeah.
Yeah, we kind of used it as a benchmark, and it's something we haven't thoroughly investigated. Like, there's other things we'd like to do here. Again, it's in my future work, but you know, something I'd like to see is like a parameter discriminator as well. So instead of having these sort of like explicit matching of statistics, treat it like a GAN training, right? Where you have an adversary that looks at parameters and said, did this parameters come from SGD, or did the parameters come from one of these GHN models, right? And you're trying to drive, sort of let the network figure out a way of fooling the discriminator such that it thinks it's like real SGD parameters. But again, that's starting from that's coming from the starting point that there's something special about SGD, and the parameters coming out of SGD are, you know, what we really want. I don't know if it is. We know that SGD works.
Yeah.
But parameter spaces are very, very, very high dimensional. So there could be other distributions that we haven't found by SGD that are worth exploring.
I mean, I guess the other thesis might be that I think you could do this by reversing the nesting of your loops. So basically, if you instantiate a model and then train it on SGD without changing that model, just allow backprop within that instantiated model, then what your hypernetwork would learn is a set of parameter distributions that didn't have an exploding gradient.
Yeah, right? That's an interesting possibility as well.
Yeah.
Yeah, I agree.
Cool. Yeah, I definitely agree that that's a really open space, right? So we don't know whether we're kind of whether we've done so much gradient descent by grad student in figuring out all of these tricks that we're stuck, or whether we should expand.
Does the HyperNetwork choose its own optimizer, or it's like a Adam optimizer by default?
We use SGD.
SGD.
So,
the SGD.
Yeah. We use what we're trying to replace. It's kind of a weird philosophical thing, but yeah, we train it by SGD. Okay, so I'll move on. So another the final improvement we make to GHN2 is that GHN1 really looked at a single architecture at a time for doing updates for each batch of images. So you choose an architecture, you feed it, you predict the parameters, feed a batch of image, then back propagate. We use batching, and we found that larger batches tend to reduce the gradient noise, just like it does in sort of vanilla SGD training. So we did some experiments where we can compare batches, and it's not just a function of seeing more data. So that's what we're showing sort of at the bottom plot here. We kind of normalize for the total amount of examples you see. So for example, we train with batch size 8 at 300 epochs versus batch size 1 at 2400 epochs. And we do see some stabilization, you know, which is what you would expect, because people tend to get better results with large batches in normal training. Okay, so results. How does it perform on CIFAR 10? So on CIFAR 10, we get pretty good distribution, out of distribution, in distribution, out of distribution accuracy. And on average, we obtain results similar to 5,000 SGD steps. Again, we're just making a single forward pass to predict all the parameters. So I want to point out, you know, the speed at which we're achieving this. So like it's basically taking like a fraction of a second to do prediction, whereas you know, training with SGD is in the order of at least on CIFAR 10, we're talking minutes to hours. The other thing I want to point out here is that you know, on average our architectures are getting sort of mid-60s%, but we do find certain architectures that have as high as 77.1% accuracy. And then when we test the model on wider or deeper or denser, these out of distribution architectures, we see that they still perform reasonably well. The only one that didn't perform very well was the vision transformer on CIFAR, but we get better vision transformer performance on ImageNet. It just might not be enough data. CIFAR is relatively a small data set. It just might not be enough. Others have observed this effect with vision transformers in CIFAR as well. So on ImageNet, which is a much larger, more substantial data set, we see, again, good generalization to unseen architectures, even if they're out of distribution. Not that far off from a SGD architecture trained for 5,000 steps, and 4 to 5 orders of magnitude reduced computation.
Yeah.
Then, did I hear, was there a question?
Yeah, sorry, it's just me again.
Yeah, no problem.
In that last slide, presumably there's a number of epochs for SGD training of AlexNet that hits, 27% accuracy. I'm curious how long, whatever number of epochs that is, how long that takes and how that compares to 0.3 GPU seconds.
Yeah, I don't know. We could get out the calculator and sort of linearly interpolate it, right? Like I think it would be I don't
not quite linear though, right? I mean the descent curve is very steep at the beginning and very shallow later.
Yeah, I don't know if cutting, yeah, I guess you're right. Like 100 epochs is probably beyond the linear part of the descent curve. And so it's probably close to convergence.
Yeah.
On an AlexNet. That looks like AlexNet style performance on ImageNet. So yeah, I don't know. Like one thing to note is SGD 5,000 steps. So we're talking about steps versus 100 epochs.
Oh,
so
yeah.
It's something in between, right? So it's something like, I don't know, maybe like 10,000 steps, I would say, of SGD.
Okay, but that answers my question. You're better than SGD of 5,000 steps, even when you're using like 0.01% of the computer.
Yeah, I think the reason we picked 5,000 steps here is we were trying to approximately match the out of distribution performance, and you might be trying to get us to match the in distribution performance, for example. We could have also matched on that.
Great. That answers my question. I think I just didn't read closely enough. Thanks.
Okay, cool. Yeah, so another benefit of GHN is that we can use it as a general purpose initializer for arbitrary neural nets. So you're probably familiar with the H method or the Glorot method of initialization, which are random init methods. What we found is that in low data environments, the GHN is a good initializer. So we did this in 2 tasks, like a few shot image classification task and also a few shot object detection task. And we compared our results to pre-training the same network on ImageNet, which is a much more costly procedure. And the one issue that we're finding here, and I'll mention this at the end, is that in the larger data setting, if you have access to all of CIFAR or all of ImageNet, and you attempt to predict the parameters and then you go and train by SGD, something goes wrong. It's not a good general purpose initializer in the large data regime. And the way I think of this is like, imagine we discovered this procedure for training babies, and we could sort of like give them the ability of a toddler within a few weeks, right? And so like we had these like, I don't know, 6-year-old infants that were acting like toddlers. I'm saying they're not acting like adults because our GHN are producing 60% accuracy on CIFAR. It's not a net that you would want to use and deploy, but it's pretty good. It's like a toddler network. So imagine we could sort of like give toddler ability like really quickly to babies, but then we went and tested them later in life and tried to see how they're doing as adults. Something would have gone wrong. Like they wouldn't do very well in life. They would suffer some issues in terms of how they absorb information. And so that's kind of what's going on here. Like we've found a way of sort of short circuiting to like toddler level behavior. But then if we just sort of do the usual training procedure from that point onwards, something goes wrong. And this is another open question for us, is like, are we getting into some weird part of the parameter space that causes us to be able to, basically causes us to not be able to recover from that. So anyways, that's one of the things we really want to understand better about this is like, why can't we just take a predicted parameters and then train from there on for SGD? It won't recover the same performance as going SGD all the way.
But how should we think in terms of the model space? You know, how like,
Yep.
because you like what's the limit of, you know, how because we could see maybe there's some models that I mean the HyperNetwork has not seen before, and if you give like a better model, it get better. So toddler becomes a bit better than a toddler on.
Yeah, I don't know. I mean, we tested all these OD architectures, and I think this effect was observed in everything that we tested it with. But we certainly, I mean, we're restricted to basically this picture I showed you, which was the, you know, these darts types architectures, the model space. We didn't really go beyond this, but it could be that if we tried something very different, we might observe different effects. Okay, so then I think, you know, this is the last result I'll show you, and I'll start wrapping it up because I know we're about 5 minutes to go. So I thought this was also a nice use of these models, is doing property prediction. So we have learned a strong representation inside the GHN of neural architecture. So we can give it a computational graph, we can get an internal representation from the GHN, and then we can ask it questions about that computational graph or about that architecture. And so we can rank architectures by different properties. So we can search accurate networks or more robust networks, networks that are fast to process images, or networks that are fast to converge. And all we need to do is just basically put an architecture into the trained GHN. We do some averaging across the nodes of the node representations, and this gives basically a vector-based embedding of that architecture. And so we can do neural architecture search this way by using these sort of performance predictions. And this is what we get. We get compared to an architecture called the neural predictor, which is specifically designed for this task. Our GHN is actually very good at predicting the accuracy that an architecture would achieve on clean data or Gaussian perturbed data, or its inference speed or its convergence speed. So it's a good predictor of how that network will perform in deployment. And we did a sort of a reduced compute neural architecture search using this technique and got an architecture that performed 97.26, which is basically state-of-the-art performance on CIFAR 10. And this is way, way, way faster than actually doing sort of old school NAS, where you have to actually train architectures to convergence. This is all done by sort of less than a second parameter prediction. Okay, so to wrap up, I showed you that, you know, fine-tuning the parameters worked in 2 low data tasks, but it fails in the task of more data. And this is the sort of baby toddler thing I was telling you about. Our GHN2 is in orange. It's just kind of never hitting the capacity of the SGD trained models, which you see in green there. Sorry, the fine-tuned model is in red, so it's sort of between the GHN and the HUT in its sort of standard SGD model, but it just never reaches its performance. I mentioned also that we use a fixed data set and a fixed objective. One advantage of iterative optimizers like SGD is that they're very flexible. You can adapt them to new data sets. You can do multitask. You can do sort of all sorts of different combinations of tasks and data. So it would be nice to do parameter prediction with, say, self-supervised objectives, or do sort of multi-data set type work. And that's where we hope to go. So if you're interested in checking out the code, here's our website. There's a picture of the Colab notebook. We've released this DeepNets 1 million if you want to do something with those, that data set of architectures. And now I show you how to do parameter prediction in 1 second on a CPU. And I showed you, it's not a state-of-the-art architecture by any means, but it's useful in neural architecture search. It's used for property prediction. And there's many things that we're interested in doing in the future, like making it better, like approximating SGD performance, improving the fine-tuning, figuring out why fine-tuning goes wrong, and then also understanding why these GHNs work. And then maybe this will give us an insights to even improve on SGD training. So that's it. I guess we're on time, but took a lot of questions along the way, so we probably don't have a lot of time for questions now, but thanks a lot for joining and for all your great questions.
Oh, that was excellent. Yeah, thank you very much. I think we checked your website, and if someone wants to, they can check the code. I mean, I like this graph. It reminds me of. So it looks a bit. I mean, it has nothing to do with it, but it almost look like this AlphaFold. This like DNA.
Oh, the architectures.
The architectures, right? And the small. Each step look like amino acid. But
they're pretty. Yeah, absolutely.
They're very pretty. Okay, thank you very much, Graham, and I hope to have you again. One day if you have something on the biodiversity, like maybe.
I'd be happy to chat on biodiversity in a future talk.
Yeah. Okay. Okay. Thank you very much, and thank you everyone. Thank you, Alex, for your help and all your insightful questions, and we'll talk another time. Okay.
Okay.
Thank you. Bye bye, everyone. Bye bye.
Thanks so much, Graham.
Bye bye.
Bye.